Hi everyone, and welcome to this 9th episode of the Mandlbaur Insanity. In this episode, we are going back to John's beloved ball on a string. He thinks that this is the only relevant experiment and refuses to apply his fake theory to other systems that clearly prove him wrong. Okay then, let us keep working on his ball on a string. When we pull on the string in order to shorten the length, we are doing some work on the system and therefore we are adding some energy to the system. I ask him a very simple question. Where does this energy go? He refuses to answer, claiming that energy is irrelevant. How can it be irrelevant since his claim is that angular energy is conserved? That should be the most important quantity of his theory. According to his theory, the energy of the ball remains constant. So the conclusion from his theory is that the energy that we are adding magically disappears. If instead we release the string, then it is the system that gives us energy. But then his theory implies that this energy comes out of nowhere. In other words, his theory would imply that his ball on a string is a free energy generator. Of course, as we know, the guy is a liar and a coward. He always flees when we make him face these inconsistencies. So, in this video, I'm going to prove that the energy that we put in goes into rotational kinetic energy, and therefore his angular energy is not conserved. So let me recall that John's obsessional ball on a string is a conical pendulum in the particular case where the angle between the string and the vertical is 90 degrees. Therefore, all general properties of a conical pendulum must apply to his particular case. He claims that this is a lie, which proves again that he has a very poor understanding of physics. Anyway, whether the angle is 90 degrees or not, the following discussion applies in all cases. Now, when the ball spins in circular motion, its displacement is perpendicular to the force of tension in the string, so the string doesn't do any work. We all know that John totally ignores what torque is, so we are going to consider that the experiment is performed in a vacuum chamber where the torque with respect to the center due to the air drag is totally absent. In that case, our 340 years old theory says that angular momentum is conserved. Now, what happens when we pull on the string? The forces line of action passes by the center, so the torque remains equal to zero and angular momentum is still conserved. But this time, some work is done because there is now a displacement towards the center, hence parallel to the applied force. If we use a string whose mass can reasonably be neglected compared to that of the ball, then the force that we apply on the string is equal to the force that the string applies on the ball. This force is easily calculated. Indeed, the centripetal acceleration is equal to the radius times the square of the angular velocity. Then Newton's second law implies that the force that we are applying is equal to the ball's mass times this centripetal acceleration. Knowing this force, we can calculate the work done by integrating it over the displacement from the initial radius to the final radius. You can notice the negative sign that is there in order to take into account the fact that the differential element dr is negative, so that the work done is positive as it should be, since the force is in the same direction as the displacement. Before integrating, it is important to pay attention to the fact that the angular velocity depends on the variable of integration, r, so we need to include the explicit dependence. This is easy thanks to our beautiful law of conservation of angular momentum, which allows us to express the angular velocity at any time as a function of the initial radius and initial angular velocity and the radius at the same time. Plugging this back into the integral, we can now explicitly calculate it and we obtain this expression. Now we can apply this expression to his yo-yo, which by the way looks pretty light. So let's assume that its mass is 20 grams. He also insists on reducing the radius down to 10% of its original length, so we can start with 1 meter and go down to 10 centimeters. He also likes the initial angular velocity to be 2 rands per second. If we convert all these in SI units, that gives a mass of 0.02 kilograms, an initial radius of 1 meter, a final radius of 0.1 meter, and an initial angular velocity of 4 pi radians per second. If we plug these values in our expression for the work done, we obtain 156.3 joules, and this is the energy that we added to the ball. Once again, according to John, this energy magically disappears since he claims that angular energy is conserved. But let us see what conservation of angular momentum says. Conservation of angular momentum predicts a final angular velocity of 400 pi radians per second. This is his obsessional 12,000 RPMs that are at the origin of his mental breakdown. If we calculate the kinetic energy change that results from going from the initial angular velocity to this final 12,000 RPMs, we find a change of 156.3 joules, exactly equal to the energy that we put in. This is where the energy goes, Mr. John Mandlbaur. Once again, you have been proven wrong.